Well, thanks for sticking this out, and it's a pleasure to talk to you about this project I've been working on with a number of people on the Mini RF team to take into account the incidence angle of the observation on the data. So, as many of you probably heard yesterday, Mini RF is a radar that is flown on the Lunar Reconnaissance Orbiter. And in its monostatic configuration, when it had an active transmission, it took many thousands of collects in 2010, 2011 timeframe that produced this incredible data set of the moon in S-band and X-band. And I hope, Garrett, you saw Gareth Morgan's presentation yesterday, because I'm not going to tell you all about that in detail, but I do want to tell you about some of the quirks of this data set. One of the quirks is that it has to date not been tied exactly to the lunar reference frame. So when it was initially processed, it was processed onto a sphere. And so the tying of the data set to topography of the moon was tricky. And also there was offsets of up to kilometers of the position of pixels relative to, say, the SLDEM or other Lola reference frames. And so that's kind of annoying if you want to compare it to other data sets. It also meant that we didn't have a local incidence angle backplane where we would know where the radar wave was impinging on the topography of the actual surface for the data. And so I've been working on trying to make progress on that. And to do so, the basic method I've been using is to take the data that exists now, tie it to a high resolution shape model, and then predict what I think the illumination would be if it was where we thought it was. And it turns out it never is, right? So that you don't get that match, but it's close enough that you can cross correlate that predicted model of the illuminated surface with the actual data and get a decent offset between the data and the real lunar reference frame. And once you've done that, you can translate the position of the Mini RF data into the correct place and get a nice orthorectified image like this, where the crater topography shows up in the shape of the collect. And so you've gotten a good position of the data onto the surface. So I've now done this for all of the monostatic data, the S-band and X-band data. I'm only talking about S-band today for time, and mostly because I'm mostly interested in that. If you've ever used a radar system before, if you've ever even taken a look at Mini RF data, you know that the incidence angle is a dominant factor of what the return signal to the instrument is. And so this makes a lot of sense. You're shining basically a light at the surface in radar wavelengths. And as the slope is facing you, you get more direct reflection at lower incidence angles down below 40 degrees than you do when the slope is facing away from the instrument at higher incidence angles. And we see this dramatically in the data set with the radar power. S1 just basically means the power of the data of the detected signal. There's some spread that I don't fully understand yet. At the nominal incidence angle of 49 degrees, which is when the radar was seeing a flat surface on the moon, there's some spread still in the detected signal we get back at the instrument. And that's a combination, presumably, of how strong the output signal from the antenna was, combined with some amount of difference on the surface in the radar reflectivity of the surface. But we think from other observations that the moon doesn't vary by many factors in radar reflectivity. So I've taken the liberty of normalizing out this difference that exists at 49 degrees in each collect. And then you see that all the S1 data basically collapse onto a fairly neat function, where there's a steep power law branch at lower incidence angles, where you're getting a specular reflection of the radar wave back to the instrument, and then a more cosine-like behavior at higher incidence angles. And CPR also has a strong relationship with incidence angle, so that you get much more direct specular reflection. You get one flip of the polarization at low incidence angles, like you would get off a mirror. And you get more of the same sense circular polarization at higher incidence angles, where you get multiple bounces. And so what we can do is take out this incidence angle signal by figuring out what the incidence angle of a collect is on the surface, figuring out what we observe in the CPR, and then subtracting the model that we have here now for how the incidence angle affects CPR from the actual data. And in doing so, we get a normalized product that's basically equivalent to the CPR that you would expect if the observation geometry was at 49 degrees at every pixel. And so this makes craters pop out more, and also removes the effect to a large extent of the high incidence angle when you're illuminating from the right here on the inside of this crater. And so what we can do then is make mosaics. And so on the left is a mosaic that's just east looking that was produced prior to this correction. And the right is the correction once you've taken out the incidence angle effects. You can see this is kind of messy looking on the left. It has lots of instrumental effects of how the incidence angle changes over the collects. And also it just doesn't mosaic very nicely. Whereas once you take this into account, you get these nice smooth mosaics that really reflect geology. And this is the other look angle to just give you a sense that, you know, if you really do see two different things, depending on the incidence angle you look at the surface that goes away once you take into this incidence angle correction. And so this is the North Pole and the South Pole of the moon. I know we spent a lot of time at this meeting and over the last few years as a community looking at the poles of the moon. And there's a lot of really interesting dramatic stuff that stands out here that I don't have a ton of time to talk about. But one thing that stood out to me is that the area where Viper is going to land is actually a high CPR area. And we think this might just be a high porosity region where the porosity might increase from, say, 15% or 20% over the upper meter to 40% or something. You can do it with just porosity without having any description changes in other characteristics. There's also these big sort of large scale regional changes where Cabeus is a low in CPR that's been seen before. And things like Faustini, Hayworth, and Shoemaker are slightly higher in CPR. And so we've done this over all of the collects. Like I said, this is the global mosaic. I've now submitted this paper this week, which is great. So hopefully we'll be able to get this into quick map soon so you all can analyze it. Hopefully we'll get the data, raw data out as well. This is the CPR product. You can see all kinds of structure in this map too. This SPA is high, and so are the highlands. The highlands are relatively high compared to the Mare for reasons I don't understand still. And what you can do with this data is then apply it to places where we're actually potentially going to go. So Gareth showed this yesterday. This is the place where many of us spent a 2 months really staring hard for the A3GT activity right at this crater here. And if you take this incidence angle correction into account, you really see the pixels inside this crater pop. And those are areas where there's just beautiful rocks in L rock. And so you can use this normalized product as a way to guide your eye to the places that have the highest CPR and the highest roughness and rockiness in like an L rock product. So I'll leave it at that. I just wanted to let you know that this correction is ongoing. I put this paper in, and I think the correction really helps accentuate geologic variability relative to just sort of the radar observational characteristics. So thanks.